Okay. Now, these three structures, modules, component connectors, and allocation structure, I do not want to spend too much of time during these sessions because they are beautifully covered in the pre-recorded lectures that have been provided to you. But still, we'll go through it very quickly. One of the module structures is called a decomposition structure, where you decompose the entire application into submodules. Now, the units in a decomposition structure has a relation of is a submodule of. You decompose the original module, so each module becomes a submodule of another module. And these modules can be decomposed to smaller modules, smaller into further smaller modules, and ultimately you land up at the code level. Modifying the code becomes very easy. Changes get localized when you divide into modules. And in a project organization, this structure helps you to build up a test plan. It helps you to integrate the project into an element. And sometimes these modules are called subsystems, somewhere they're called segments. So this is basically what decomposition is about. So this is the form of a module structure. Another form of a module structure is called the users structure. So in a user structure, this module uses that module. See, in the previous one, decomposition, the module was a submodule of, was a part of. But here, there's a usage relationship. So normally, when there's a usage relationship, you can use a test rack or a stub to test a particular unit. Java gives you a concept called unit testing, so that each unit can be tested independently based on its relationship with other unit. So each usage structure module provides a functionality to another module. So this is what a usage structure is about. And the beauty about usage structure is you can develop each unit at a time. And the unit can be tested on a test rack, and sometimes you can use stubs. A stub is a dummy program which provides a response just enough to test the system. I'll give you an example of a stub. Say you are writing an online system where there's an online payment involved. Now, you do not want to actually do online payment to test this online payment module. So what you do is you create a stub. The stub emulates the bank's or the credit card's payment gateway. And it allows your programmers to test the payments using the stub. Now, the stub should be properly written. Probably the stub has been kept by the company for use by a number of applications. They prepared the stub and kept it. So after testing with the stub, if it runs fine, then the final testing could be done on the live gateway. So for every gateway that you are using, you could use a stub to do the testing. And sometimes there are the reverse usage relationship. You have written a unit which is used by another unit. So you have a test rack. The test rack provides inputs to test this particular unit. So in Java we call it the unit test. The unit test code is automatically created to test a particular functionality. So if you write a class with a number of methods, you can write a unit test to test whether the functionalities are being provided or not. So these modules which are written, which work with each other, are said to be in a users relationship. You'll notice I'm not taking too many questions just now. The reason is that I would like to be able to flow through this class today, and whatever doubts are coming up in next Saturday's class, I will start off by covering up these doubts. Okay, so rest assured that everything that you put down there will be addressed, but I want to maintain a certain pace today. And many of the items you're asking may probably get cleared automatically in the course of a lecture. Another type of a module structure is a layer structure. Those of you who have done some preliminary courses in software would know about the internet, and in the internet, the entire structure of the internet is layered, starting from the application layer where the application runs and ending at the physical layer where the data actually moves over either wire or Wi-Fi. In between you have the data link layer, you have the transport control layer, the IP. So each layer performs a unique functionality and it works with the layers corresponding to it. And these layers, they envelop the data as it moves over the layers and then dispatches it physically. On the receiving end, it opens up one envelope at a time. So this is a beautiful example of dividing an application into layers. Similarly, a layer structure is used by the Android operating system. It divides the functionality into layers until the last layer interacts with the machine at the Linux kernel. So you divide an application into layers to make the working better. So you have a different method of dividing into module. One was called decomposition, the other was called uses, this is called layers. So decomposition was simply dividing one box into multiple boxes. Uses were dividing boxes which use each other. In a layer, you have code which uses the layer below it. So the top layer uses the next layer, the next layer, the next layer, and that way we percolate down through the layers, and we divide the entire application into components called layers. And the beauty with layers is that you can give it to separate developers. Why separate developers? There must be people here who are working for Cisco. Cisco conventionally was working in just one or two layers. There will be a company working just in the data link layer. There will be a company working just at the physical layer, just providing infrastructure to physically move data from one location to another over Wi-Fi or over GPS or over cables or over optical lines. So they are working at the physical layer level, and applications that interact at the physical layer level belong just there, and they don't have to bother about the other applications. So strictly dividing it cuts down complications. You don't try to do too many things at one place. So this is a layered structure. Mind you, you have the generic is the module structure, decomposition, usage, layer, they are type of module structures. Then there's another module structure called the class structure. Object-oriented programmers divide an application into classes. And this division, each class is a module. So you have the class-based hierarchy, and that's also a module structure. Then data models. You create a data model where you have entities and relationships between the entities. And those of you who are working on RDBMS would be drawing something called an ER diagram. An ER diagram is basically dividing data into modules. So it is very much a module structure. Okay, somebody wants an example of classes. Say you are writing a video game. A video game has got the ball class. If you are having a ball game, goalpost class, footballer class. So various classes are there to take care of various aspects of the application, and everything to do with the ball is coded into the ball. So that becomes a module. So this is how the class hierarchy divides an application into modules, and each module we call a class. Somebody asks, should an architect be working at the class level? Definitely not. But definitely this is one of the type of structures for breaking up. And sometimes what happens is that classes together, they create a package and they work in a group. Now, a package working in harmony along with the controller class can operate as a unit in software architecture. So the dividing line sometimes becomes very thin between design and architecture, but whatever needs to be decided early, whatever determines the structure of the software system becomes architecture. Now we come to some component and connection structures. Component and connection basically talks about services being offered by various units, the way the services interact with each other, and whether they work concurrently or they work synchronously. Asynchronous systems work concurrently. Somebody asked whether the network layer is an example of a layer structure. Yes, the network layer is definitely an example of a layer structure. Allocation structures. We've discussed earlier, we mentioned it once again, assigning to hardware elements, assigning to communication channel, assigning to CPUs, assigning to working teams. All these assignments amount to allocation structures. So every allocation of software to a resource is an allocation structure. So deployment could be one such structure where you deploy software systems to hardware processing elements and to communication elements. So that's a deployment structure. Implementation structure will be assigning modules to and mapping them to, say, file structure or system development teams or configuration environments. This would amount to implementation structure. Work assignment structure will be assigning it to teams who will do work. Somebody wants to know whether the slides will be shared. Yes, they will be shared within the next 2 to 3 days. So, in this, one of the allocation structures is your work assignment structure. And work assignment structure takes care of assigning the work on various modules or components to various developers, to engineers or coders, whatever it may be. Now, these structures, they don't work in vacuums. So, I'm getting a lot of questions here, and I think what I'll do is, based on all these questions, I will work out a short script and I will answer it in the beginning of next Saturday's deliberation. So, definitely these structures, they interact with each other. There is an interaction, just like a physiological structure. Your circulatory system, digestive system, your skeletal system, they are independent, yet they are dependent on each other. They take resources from each other, they use each other's environment, and they facilitate each other. Similarly, different software structures provide you an interconnection with others. You work out a component and connection structure, then use it in the allocation structure. You do a module structure, use it for component and connection. So these type of interrelationship between the systems exist. So just take a look here. Now this is not quite UML. Anything that can express is a good architectural diagram. So decomposition. You take a system, divide into client into server. Each one is a module. So it's a decomposition. And client server, if I want to show it as a component and connector, here's the server and your various components. So I've shown the components, and a request reply is the connection. So this becomes the client server view as a component and connector view, and this becomes a decomposition view. Same system, you have shown two different views of the system. Now, briefly, I want to introduce you to the concept of architectural patterns, which will be covering much later in the course. An oft-repeated question is, sir, where does software architecture end and where does object-oriented analysis and design begin? Well, the division is tough. Let's say those decisions which are more coarse in nature are taken by the architect, leaving the details to the analysts and designers. Software architects do get involved in the software development life cycle, but they get involved at the early stages. Some very senior designers do become software architects. Thereafter, the architect keeps a tag on the development life cycle to make sure that in implementation you are not deviated from the intended architecture. That becomes very important. Now, as a result, architectural pattern is a pattern of usage of components in a standard manner to get standard results. And what do you mean by standard results? Standard results in terms of quality. That means availability, performance, modifiability. So certain type of arrangement of components have a habit of giving you certain benefits. And since you know that benefit will accrue in a given situation where you have a given type of a requirement of qualities, you will select a pattern, that means a formation of these modules between themselves to be able to deliver. Now, it may be difficult to understand in abstraction. I'll give you a few examples of architectural pattern. A broker pattern is an architectural pattern. Pipes and filters is an architectural pattern. Layered pattern is an architectural pattern. Blackboard pattern is an architectural pattern. Model view controller is an architectural pattern. Presentation abstraction control is an architectural pattern. These are standard names given to certain methods of formation of software. Client server is an architectural pattern. Now, these are standard formations of blocks which are known to give certain desired results, and that is what patterns are about. Now, there are certain patterns which fall in the component and connector category. So, shared data. Shared data is a pattern where a number of applications may place data in one place, maybe in SQL Server or in Oracle, and all of them will access the shared repository. Windows may have a shared repository in the form of a Windows registry. That's a shared data, where you have the key value pairs. It's a very popular method of storing data these days, key value pairs. And the Windows registry is one place where data is stored as key value pairs. Another popular component and connector type of a pattern is the client server pattern. Client server pattern became extremely popular in India a couple of decades ago when hardware was considered very expensive. So you use a server either as a data server to store a lot of files, a file server, or as a database server to run an RDBMS, or as a mail server to handle mail. And then all the clients interacted. Initially, they used to interact over dedicated lines. Gradually, we've had sophisticated networks. The Novel Netware was a very big company which provided network solutions. And today, of course, the TCP/IP based protocol for networking is probably the most popular protocol on the internet. And large number of systems are connected in various formations whether on client servers or peer-to-peer or round robin. So you have various types of round robin is now virtually obsolete. It was a very popular architecture with IBM at one time. So today, by and large, it is TCP/IP, and you have a lot of client server usages. You have a lot of peer-to-peer networks in operation, and these are basically component and connector solutions. Then you have allocation pattern, multi-tier pattern. And allocation, we've talked enough about allocation, we can leave it off today. Now, what makes a good architecture? So, inherently, there should be nothing good or bad. Somebody says something is bad because he expects something else. A very good way to understand is that we have 10 people. There's a gold medalist from 10 engineering colleges in, say, computer science. So there are 10 toppers from 10 engineering colleges, the best engineering colleges in the country, and they're all toppers. And there's one person who is a second divisioner. It just so happens. And then he gets the job. And then there's a big hue and cry that there's the whole selection process is rigged up. They take their own people, and this is all a farce, the interviews. And on investigation, it was found that the only person who had no clue of who was in the company and he didn't know anybody was that one person who was a second divisioner. Then why did he get the job? Because he fitted the job. So there's a concept of something called fitting, and so with architecture. And architecture has to fit the purpose for which it is intended. A candidate has to fit the job. Every job is not a reality competition. It's not a selection for Mr. India. It is a selection for a person who is right for the job. And so with architecture, we have an architecture which is right for the job, and an architecture which is not right for the job is normally referred to as bad architecture. So, and it's very important as an architect to make sure that the goals are stated goals. The goal should be stated. And that is where an architect has to bring in a lot of maturity. He has to get the stakeholders and has to get them committed to the requirements, and then deliver an architecture which delivers on the requirements. Now, there's a rule of thumb given here. The rule of thumb is that a work of art, and to some extent an architecture is a work of art. It's a work of art by a technically competent person using all the scientific and technical principles. But the same problem can have more than one solution. So you've got to have one leader. You cannot have an architecture developed by two great architects. You have the best architect from Europe and you get the best from America, and then you say you come up with an architecture, not likely to happen. One of them has got to be the leader among equals. Then an architecture depends on the agreed quality requirements. If the most important requirement is security, the result is going to be different. If your most important requirement is performance, you're going to have something totally different. If the requirement is usability, we are going to look for a different solution, modifiability, testability, each one. Now, I mentioned a little earlier also, the project manager and the architect work very closely together. Very often, they don't possess the same talent. You could have a good architect who is also a project manager, or a good project manager who also happens to be an architect. But the reality is that a project manager requires distinct talents. he is a time manager, he's a man manager, he's a money manager, whereas an architect is a technical expert who understands how to deliver quality attributes. So nobody's stopping somebody from having more than being multi-talented, but assuming that a project manager is the definition of a talent and architect is the definition of a talent, we've got to get them to work together very clearly. And architects do like to do incremental development. They take the most significant attributes first, they develop this system, and they leave certain decisions for later. But only minimal functionalities can be left for later. And very often, when an architect is working regularly with the same design team, they have a better understanding with each other. And if there's a good understanding between the design team and the architecture, most of the fine-grained aspects are taken care of by the design team. The architect may not have to get involved. Now, architects who have worked with design teams, they make sure that they provide the type of features we look for in object-oriented systems. Information hiding, modular design, well-defined interfaces, design by contract. These are concepts which even the architects use, just like the software designer. There's an aspect which is relevant here. We'll go into more details later. There are sometimes constraints imposed by the stakeholders, and in spite of the requirement of quality attributes, there may be constraints where the stakeholder says, "Oh, you've got to do things this way," and there are times when the architect has to get back and tell them that if it is to be done this way, then this is not going to happen. So an architect has got to have a very, very clear perception of what he's trying to deliver. Now, here a few warnings are given that you don't have to one-to-one correspondence between module and components. A couple of modules may make up a component, and the architect has got to indicate for the major components how they interact with each other. And right from the very beginning, the architect has got to start giving directions or indications, let's say, to the project management team as to how contention of resources, or how to resolve certain allocation issues. He's got to address them right up front in the beginning. So these are the type of little key tips, and we'll be going into much more details on all of these later. With this, we finish off this small session which we had on introducing architecture, and I'll just take a 2 to 3 minutes break, and we'll start off the next session.